Vanilla latte served to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte served to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte served to go. I drink it slow. Morning coffee.
What up, everybody? Welcome to Coffee Hour with Paul. Hey, it's great to have you here. Thanks for joining me today. I know it's a Saturday morning. I know it's early, and it's your day off. Or some of you out there that are hustling are probably working today. Probably the basement kings, probably out there getting the trucks ready and getting everybody out on the road. But thanks for joining me. Got my coffee. Hopefully you got yours too. We're going to have a great conversation today on Coffee Hour. But before we get started on Coffee Hour, I want to tell you a couple things that are coming up on future Coffee Hours so that you're aware of it. We have got a bunch of shows lined up on my task board. We're going to be gearing it back up with a bunch of different topics on the National Electrical Code, covering many things. But hopefully you're listening to our podcasts. Now, podcasts by far are our broadest platform that we have the most listeners. We still average about 300,000 downloads a month of our podcasts across all of the platforms. But one of the more popular ones is Let's Ask Paul, and that is a podcast where you can go to paulabernathy.com and you can submit a question. I have a backlog of questions, and I'm trying to get through them all. Some of them we will answer via email, and others will be answered in a podcast directly. So we'll answer your questions that you have, and so be sure to check that out. And when would you listen to the podcast over watching the video? Well, I do more podcasts than I do videos. One, it's a little easier to do a podcast because I simply have a topic, I cue up the mic, and I just go. And most everything that I do is a one take. I don't like to do multiple takes. And I don't put all the editing effects and things in because I'm just there to teach code. And so typically the base that would follow me is they're only code. So I'm not trying to get the other stuff. I'm not teaching you how to bend conduit. I'm not teaching you all that stuff. But that's the exciting news. We will be showing some videos of me with the hands-on, doing certain things in our new facility that we're getting at Encore Wire Corporation, whereas I'm going to be able to do some training and things like that. So I'm excited about that. And do me a favor. If you're in the chat and you want to shout out where you're at. John from Omaha, Nebraska. Welcome, John. Thanks for coming this morning's Coffee Hour with me. So where can you watch Coffee Hour? You can actually watch it on all of our Facebook pages, our YouTube channel, obviously. That's where John's watching from. You can watch it from Twitch. You can watch it from Twitter. You can watch it from LinkedIn. Anywhere you want. We utilize Restream, sends it everywhere. So, and obviously all of these are recorded so that you can watch them at a later date. Robert from my own state of Texas, San Antonio. Thanks for coming, Robert. Okay. Anderson Electrical Services in Omaha, Nebraska. Check them out for those watching who need electrical services. There you go. Right there. All right, so today's episode of, I should mention also this show, Coffee Hour, is sponsored today by, where is it? Right here. by the Fast Tracks program. If you've never seen what that is, okay, what are you doing? You got to go look and see what that is all about. Guy from Vegas, okay, goes Sin City. Welcome, Guy. Thanks for joining us. So, what is today's topic on Coffee Hour? We are going to be talking about. No, John's retired now. Don't call. Don't call. He's retired. He doesn't want your business. But I'm sure John knows somebody he could refer you to. Okay. So, look, today's topic, we're going to be talking about main bonding jumpers and the importance of main bonding jumpers. Now, I will not give away the teaser in what a lot of people are probably watching the video or will rewatch this video, is about an illustration that I posted on all of our social media. Whether you're on the Sparky Hub or you're on our Facebook pages or you're on our Twitter account or our LinkedIn, whatever, we posted an illustration. The illustration, again, whether you like the illustration or not, it was depicting a situation where you had to size a main bonding jumper. Now, that illustration will be used for other things because there's also a supply-side bonding jumper there, and there's different iterations of that image that we'll be using for other types of lessons and things like that, so check that out. Welcome again. James, welcome to the stream. Glad to have you all here. Look, main bonding jumpers. We're going to look at the code, but before I even get into the code, it's important that we talk about the importance of a main bonding jumper, okay? So the main bonding jumper is what I say to me is the linchpin of the electrical safety system. Whether you can agree to disagree on the importance of it, the lack of it, meaning not putting it in or properly sizing it where necessary, means that in a ground fault condition, you are not going to clear an overcurrent protected device, okay? Now, overcurrent protected device being circuit breaker or fuse. The typical circuit breaker that we would utilize today, the typical, would be an inverse time. And again, it's proportional. So the amount of current that flows through it or that it sees, the quicker that it trips. The less amount, the slower it is to react, right? Hey, check it out. Michael Schwartzy's in the house. James from Baton Rouge. Thank you, James. David from watching from LinkedIn. Greetings, David. Sharp cat right there. He's also in our Facebook page. And I think David was the first person out of every platform to get the size of the main bonding jumper correct. Okay, so he has the dubious honor, I believe, of the first person. Now, I would say out of 99% of the people, or even higher than that, got it wrong, and that's okay. That's okay. We'll look at all that today. But David got it right, so it's sharp cat, and David's very active in the industry as well. So, and see, again, did I say Schwartzy? Yep, Schwartzy, thank you. David's in Southwest Florida, okay? So down there where it's probably really nice weather. Main bonding jumpers. So the importance of the main bonding jumper is to interconnect the grounded conductor from a grounded system into your, we'll just use a panel, into the panel. It also allows the interconnection between the equipment grounding terminal bus or the equipment grounding conductors to make a connection at the service with the grounded conductor so they're all together, right? Now, everybody thinks of a normal panel where the power is coming in, the supply conductors are coming in, and you have one bus, or you have the kind that has a bus on each side and they're connected by a bar. And we land all of our equipment grounds there. We land all of our grounded conductors, and in most cases, say residential, it'd be also neutrals. We land them there. And you don't even think about it. It usually comes with a green screw, and you put it through, it connects the cabinet to the grounded conductor, it connects the equipment grounded conductors, everything together, right? And then what happens is that when there's a ground fault condition downstream, that it allows that current to get from the potentially energized enclosure or the normally non-current carrying metal parts, that's what we talk about it, over to the grounded conductor back to the source. So it creates this low impedance path that allows that fault. At the point of the ground fault, it allows that current to skyrocket. And obviously, if it skyrockets and that amount of current is traveling back to the source, the overcurrent device, again, will operate very quickly. So if it's a 20 amp breaker, typically 6 to 7 times its rating is what it takes to activate. So obviously we're talking about thousands of amps at an instant. It allows that overcurrent device to function. Now, imagine if that main bonding jumper was not there, right? If there was no linchpin between the energized part, potentially energized non-current carrying metal parts, and that current could not get back to the source, then it would treat all of that as if it was a load. If that's the case, it's waiting for something to come in contact with it to complete that circuit. And sadly, it could be you. So by having a properly sized main bonding jumper, you're ensuring that one, it doesn't burn out, that it serves its purpose, it allows that return current to get to the source, and it allows the overcurrent device to function. Now, we all know an overcurrent protected device has 3 roles, right? Short circuit, ground fault, and overcurrent. Well, the short circuit between phase to neutral, okay. The overload, it operates, okay? It has usually bimetal part that'll bend, deform, and allows the latching mechanism to open up, or it's an electronic trip. We get that. It's the ground fault component that we're focusing on when we're providing that low impedance effective ground fault current path to allow the operation of the overcurrent, at least that feature of the overcurrent device, okay? Or the fuse, blow the fuse. So we kind of get it. So we understand the importance of a main bonding jumper, okay? So who else do I got to announce in the room here? Oh, good morning, 7 a.m. there. Boy, he's off to an early start. Nothing better than grounding and bonding at 7 a.m. your time. That's what I'm talking about. Nothing better. Check it out. The Basement King is in the house. Hasn't answered my text in like 2 days, so he must be really busy or he's just ignoring me. Welcome, King. Thanks for joining us. Claude's in the house. Awesome. Awesome, awesome, awesome. Okay. Grounding and bonding, getting our juices flowing on a Saturday morning. All right, so the first thing I want to do is we're going to kind of go to the code and build our way up. And we're going to save our infamous illustration for a little bit later. Okay, so let's go on and get started. So we're going to kind of go look at the code. Okay, so our first journey in the code, okay, and hopefully you've got your code books, is we're looking at 250.24. Now, we're going to keep it simple. We're going to be talking just like if it was a dwelling. I know that's why the king is mad at me, because I'm slow in getting the intro to kicking it with the king. It's coming, I promise you. And when it comes, we're going to be dropping it. I'm sorry, I've dropped the ball, king. Again, I'm a lazy guy, so I'm trying. Plus, that guy didn't do what he said he was going to do, so I'm going to have to create it. I gave him another shot. But check out that podcast when it's available, and it will be available over on Electrician Live Broadcast Network, okay? So, all right, so the first thing we want to do is go to 250.24, grounding of service supplied alternating current systems. Let's just keep it simple. We're talking about a dwelling, and let's just say that we're bringing the service. And so this is going to be typically a grounded system. And so we got to make these grounded system connections. So if you look at 250.24a, and it's on the screen, and it might be small for you to see, but if you got your code book, you can read it. And again, whether I said it or not, we're working off the 2020 edition of the NEC, just so we know. All right, so it says system grounding connections. It says a premise wiring system supplied by a grounded AC service. Okay, let's just say typical residential. Yes, it's an AC service. Shall have a grounding electrode conductor, okay, connected to the grounded service conductor at each. Okay, so hold on for a second. Let me make sure that I adjust this, because I see that it's not adjusted. So let me make sure I adjust it. It's probably from a different episode. There we go. Sorry about that. Okay, so it says connected to the grounded service conductor at each service in accordance with 250.24A1 through A5. Okay, so let's see here. To give you an example, if I have a grouping set up where I had a wireway and I had 6 disconnects, service disconnects, maybe 6 panels, each one of those would have a main bonding jumper. Okay, If I had just one panel, main panel, for a house, it would have a main bonding jumper. These are the service, okay? So that is typically a grounded AC system, okay, where the neutral point at the transformer utility is connected to earth, so it is a grounded system, okay? So the general rules, we got to read the general rules here. So 250.24A1 general rules for main bonding jumpers, okay? So it says the grounding electrode conductor connection, so that's going from your panel, grounding electrode conductor, guess what? It's going out, down, and let's say ground rods. So not required to be larger than the 250.66A if it's ground rods, and you're not going off to another electrode that requires a larger grounding electrode conductor, then we're okay for 6 gauge copper, 4 aluminum, but again, you can't terminate the aluminum on a ground rod because it'd be within 18 inches of the earth, so we can't do that. So we'll just say copper. And if you're preparing for an exam, always assume copper unless stated otherwise, just so you know. So we're talking about where that grounding electrode conductor connects. It says, reading it again, 250.24A1 says, the grounding electrode conductor connection shall be made at an accessible point from the load end of the overhead service conductors. That means you could connect it all the way up to the point where it changes over from the utility like a service drop right there if you wanted. It could come from the service drop, underground service conductors, or service lateral to, including the termination or bus to which the grounded service conductor is connected at the service disconnecting means. Okay, so going from the grounding electrode conductor down to the electrodes can be at many places in the service equipment, or can be on the supply side of it up to the overhead service conductors, the service drop location, all those type of things. So many ways to do that. Now, this show is not about grounding electrode conductors, right? So that's important, but it's important to know that that bus in there that connects to the grounded conductor is going to serve some roles. Things can connect to that, okay? And it all ties it back to the grounded conductor, right? Okay, so now jumping forward for that, we need to, hold on, let me make sure I continue. I don't want to lose anything here. Oh, hold on for a second. I got some screens I got to make sure I got open here. Okay, so what we want to do is jump forward a little bit down here to 250.24A4. So we'll start our journey. So this is real. That was just a premise. We'll start our journey. So here's what it says. So in a grounded system like that, now let's talk about that main bonding jumper. What is this? Congratulations. What happened here? Hey, Paul, wait a minute, hold on. I got a congratulations in the room. I got to go see what it is. Hey, Paul, haven't caught you live in a while. Just got my RW. Wanted to say thanks for all the content. It was a big help for me passing the test. Congratulations, Braxton. Congratulations. Okay. Again, there's nothing more satisfying for me is to hear about people that used our stuff, whether it's our fast tracks or my videos, to be successful. I'm here for your success. Believe it or not, despite what somebody want to think, or what somebody wants to portray, I get the most, and Jay will tell you, I get the most joy in seeing people succeed. Again, I'm going to die. You're the next generation. And carrying this stuff on, it means a lot to me. Okay, so congratulations, Braxton. I don't even have my cheers chimed up here, but I would do that. Congratulations. All right, so let's look at 250.24A4 and set this stage. Main bonding jumper. It says, where the main bonding jumper specified in 250.28, so we're going to look at that, is a wire or bus bar, okay, and is installed from the grounded conductor terminal bar or bus to the equipment grounding terminal bar or bus in the service equipment. The grounding electrical conductor shall be permitted to be connected to the equipment grounding terminal bus or bar to which the main bonding jumper is connected. All right, so this is going to be an illustration that we see in a minute. So this is where people ask me all the time. They go, okay, in a normal panel, when I have the grounded conductor that has the neutral for the most part comes in, and I have the buses on each side of the panel, right? You got the breakers in the middle, and you got the buses. This is a simple load. I'm going to take my equipment grounded conductors to that bus. I'm going to take my neutrals to that bus, and I'm happy. And I have a main bonding jumper in there. Typically a green screw connects to the enclosure. So everything is connected together, connected back to the grounded conductor, again, to clear overcurrent devices, okay? and all that kind of stuff. You get me? And voltage stabilization, because this transformer back at the source is connected to earth, and so is also with that grounding electrode conductor at your service. So we get it. But what this is saying, and we like to show this in our illustrations, and Phil shows this in all of his illustrations, is that he shows the equipment grounding bus separate from the neutral buses. And so if it's all goes to the one bus with everything's on it, then you don't really have to worry about this. But when you have a separate equipment grounding terminal bus and a separate neutral bus, and the equipment ground is what's connected to the cabinet, well, you have to connect those two together. You have to connect the grounded terminal bus over to the equipment ground terminal bus if they're not all one component. So if they're separate, and you'll see an illustration of that soon. In that case, the conductor that connects the two is a main bonding jumper. And typically that is the wire type. So when it's the wire type, or it's a bus bar, then you have to size it. Now, the good news is usually in larger equipment where this takes place, a bus bar, if it's included, is already done by the manufacturer. We don't have to calculate anything. It's already done. If it's a green screw that does it, then it's already done. You don't have to do anything else. However, if it is of the wire type connecting these two buses together, then it would have to be sized because that is the main bonding jumper. Now, also, this is also reminding us that, remember that original statement where I said the grounding electrode conductor has to connect to the same terminal bus or the connection to the grounded conductor? Well, this allows me, if it is of the wire type connecting the two buses together, then I'm allowed to take the grounding electrode conductor to the equipment grounding terminal bus. And it would be okay to connect it there rather than taking it to the grounded neutral terminal bus. But it has to be a properly sized main bonding jumper to connect the two together, okay? Now, if that sounds confusing, don't worry, I'll have an illustration. Just remember, when I show that illustration and I say something like, this is the moment, then this whole conversation will make sense. You with me? You get it? Okay. All right. So let's talk a little bit again about the main bonding jumper and the sizing and everything. So here's the main bonding jumper. It tells you right here. What is that main bonding jumper? It's got to be for grounded system. It's an unspliced main bonding jumper. Shall be used to connect the equipment grounding conductors and the service disconnect enclosure to the grounded conductors within the enclosure for each service disconnect in accordance with 250.28. Okay? So if I have a wireway and I have 6 panels, which the code permits, they're all grouped in one location, I'm going to have a main bonding jumper in each one of those panels. Okay? That's one way to do it. There. So if I have one panel, I'm going to have a main bonding jumper in there. Okay? And remember, I gave you an example of them separated. And that is okay as long as there's a main bonding jumper connecting the two together. I'll have an illustration for that if that's like, what is he talking about? Don't worry. I'm just trying to build the tone here for what we're talking about. All right, so let's kind of look here. So main bonding jumpers, we're at 250.28. Let's talk about them. We got to build up to this, right? The green screw, if it comes from the manufacturer, James, I wouldn't even let your brain worry about it. If it's a green screw from the manufacturer that's included with the equipment, then I have no worries at all that that's not going to be properly sized. I would go with it. It's when somebody gets a screw from somewhere else and tries to use a green Sharpie, then I got a concern, okay? But other than that, if it comes from the manufacturer, I am not worried about it at all, okay? Let's see here. There's a couple other questions in there. I think the King is fielding some questions. Okay, I'm not sure what other questions in there. Maybe he's, done question the green screw. Don't question the green screw. Whatever, Kings sometimes have grammar issues. I'm just saying. All right, so 250.28 main bonding jumper and system bonding jumper. All right, the material. So what can a main bonding jumper be? A main bonding jumper and system bonding jumper. Again, system bonding jumpers are for separately derived systems. They are essentially serve the same role, essentially, but they're different. So they're used for separately derived systems. Now, sizing them, they're going to use the same aspect of 250.102C as we would for the main bonding jumper, but they do serve it. Same concept, similar, but the main bonding jumper, I want you to think service. System bonding jumper, think separately derived system aspects, okay? All right, so for grounded systems, main bonding jumpers and system bonding jumpers shall be installed as follow. A, material. Got to be the main bonding jumper and the system bonding jumper shall be copper, aluminum, copper-clad aluminum, or other corrosive resistant material. And this would account for the screw, because that would be an other corrosive resistant material, because I'm pretty sure it's not copper or aluminum screw. Okay, so kind of covers that. It says a main bonding jumper and a system bonding jumper shall be a wire, a bus, a screw, or similar suitable conductor. Okay, all right. So we're pretty much, when I see switchgear, I usually see a link, and it's usually the same, made up the same as the bus. Okay, whether it's an aluminum bus or a zinc-coated copper bus or whatever it is, or silver-coated copper or whatever it may be, that's usually built into the equipment, and it comes with the equipment. In smaller stuff, 200 amp services, 400 amp services, usually the manufacturer sends you the green screw or some kind of Z-bar, zinc-coated bar, or something that comes from the manufacturer. And we just use it. And when we use it, we don't size it. We don't have to worry about sizing it. It's done. Don't let your brain worry about it. It's only when we end up installing the wire type that we really have to worry about this. There's probably some other exceptions to that rule for copper buses and things, but for me and you, we want to keep it simple. It usually is when it's the wire type, that's when we start to really have to do a little bit of thinking about that. And that's what we're going to do today. So at the end, the construction, it says we're at B now. It says where the main bonding jumper or system bonding jumper is a screw only. Okay, so that's, might come from the manufacturer. Will come from the manufacturer. It says the screws shall be identified with a green finish that shall be visible with the screw installed. Makes sense. You got to be able to look at it. And remember, if it's a remote distribution panel downstream and you got 4 conductors running to it, pull out that green screw, save it. You might use it somewhere else, I guess, on another panel. Pretty standardized. But at the end of the day, go on and take it out. We don't want to risk somebody screwing it in, that type of thing. Okay. The next, C, attachment. Says the main bonding jumper and the system bonding jumper shall be connected in a manner specified in 250.8. Now, if you're not familiar with 250.8, that's a list of acceptable terminations, okay? Whether it's set screw, whether it's a pressure connector, all those types. So you'll have a list. So 250.8 gives you the list. Now, again, lugs already typically come on these buses, and all this is already in the panel, so it's usually not something that we have to think about too much. That's already pretty much a given, right? All right, so now what we need to look at is the sizing. Okay, so let's talk about sizing. So we see how we get our direction. So 250.28D sizing, it says the main bonding jumper shall be sized in accordance with 250.28 D1 through D3. Okay, so if we got to size it, okay, remember that's a big if. If it's from the manufacturer, it's a screw or a built-in bus or a link that comes in switchgear, it's already done. But if we have to size it, here's what we got to do. It says D. It says we got to size it from 250.28 D1 through D3. So D1 says the main bonding jumper shall not be smaller than specified in table 250.102 C1. Okay, so it's telling me this is our first shall not rule, right? Shall not be smaller than what's given in 250.102 C1. So we get that, all right? There is a rare occasion where I have seen equipment come with a wire type main bonding jumper in it, and it was set not to the maximum size of the supply conductors, and it would have required that the wire type main bonding jumper be replaced. I'm not going to call that a mistake by the manufacturer, that type of thing. But at the end of the day, you need to be aware of that, right? You need to be aware of that because it could come with the wrong size, and you got to be savvy enough to do that. Okay. Thanks, Dave, for joining. And and having you in there. Oh, love you, have you in the CMECP. I think you'd be an awesome addition to the CMECP members. David, love to have you join that. I think you'd do wonderful in that. So anybody out there that's a master electrician that wants to take their game to the next level, CMECP program is really gaining popularity, and it really does let people know that you're not just a normal electrician. You've stepped your game up. And I don't know any other certification out there that does that for the code. Okay. So anyway, check that out. All right, let's go back into it here. So we're going to use table 250-102C1. It can't be smaller than that. Gotcha. D2 says main bonding jumpers for services with more than one enclosure. And you heard me talk about that earlier. So 230.71b is the grouping. So you can't have more than 6 grouped in one location per service set or service set of service conductors. Okay, so that's 6. So notice this says that it's going to have to be a main bonding jumper in each one of those 6 service disconnect enclosures. And it gets sized based on the largest ungrounded service conductor that actually serves that enclosure. Okay, so again, based on what's feeding that separate enclosure. And we might have an image of that later, but that's why you see 6 disconnects, 6 main panels right there in one location, 6 200 amp panels. Each one of them has the green screw, then you don't do anything. If you have to wire type, then you're going to have to size them. Now, if you're preparing for an exam, the reason we're doing this, because some people say, well, why are we doing this, Paul? Why are you even talking about it? Because the manufacturer is going to give me the screw. In my career, I have run into situations where I do use a wire type. Or you got to do this if you have the 2 separate buses in a panel. One is the equipment ground. We're not talking about remote distribution. We're in a service. I have 2 separate buses, and I have to connect them together, the equipment ground and conductor bus and the ground and neutral bus. I got to tie them together with a conductor. That is a main bonding jumper. So you do have to size that. You can't use the metal enclosure to do that. You have to size it. So that's the stuff that we want to be able to know how to do it, okay? And then, of course, D3 is talking about separately derived systems, essentially the same concept, but that's for a different show, okay? We'll be doing stuff later. I'm not going to spill the beans, but I'll be doing a separately derived system coffee hour down the road. Make sure you subscribe to the channels and get that. All right, so let's go on real quick and keep on going. Now let's jump into our course material and catch ourselves up to speed on this here. So this is an illustration that how you like that? This is an illustration that illustrates, how you like that? The main bonding jumper when you have 2 separate buses. Because I know people are asking, oh, Paul, I got to have a visual. Okay, so here's that moment. If you look at this panel right here on the left, okay, just for illustration purposes, you see the grounding electrode conductor coming from the grounding conductor bus down to the electrode. But in this case, they separated the equipment grounding terminal bus, which happens to have a green screw connecting to the cabinet, but you're required to connect them together, right? So that conductor that separates the 2, that is the main bonding jumper that connects the equipment grounds to the grounded terminal over to the grounded conductor, connects them together. And that's what the main bonding jumper does, okay? And so that is an illustration of when we would run into that situation. Of course, the picture on the right is separately derived system, which transformers, other than an auto transformer, all transformers are a separately derived system. Again, not auto transformers, but that is a totally different beast, okay? This case right here, that little jumper between the neutral point and the cabinet or the case is called a system bonding jumper, okay? Not the topic of today's subject, but you kind of see the 2. And then, of course, you'll notice downstream that panel on the secondary side of that transformer, you'll notice that that little triangle lets you know that the neutral bus is isolated and floating and not in contact with the cabinet, but you'll see the little bus on the right, green screw in there, that lets you know it is in intimate contact with the cabinet, okay? Anyway, just some illustrations for you. So we'll go a little bit further. Okay, so the main bonding jumper, as we've talked about, is important because it says the main bonding jumper are required to be a copper aluminum, copper-clad aluminum, or other corrosion-resistant material. Again, that would encompass the green screw, right? So that would be okay with that. All right. Kind of moving through these. Oops, hold on. Just closed up my screen on me. Got so many buttons to click. All right. So in this case right here, one of the examples would be, this is what I was saying, revert to the Z screw or something that might come from the manufacturer. It simply screws into the panel and connects into the bus. And that is your factory supplied main bonding jumper. And I don't have to worry about recalculating this. This is done. I don't do anything with this. Simple, easy peasy, right? Okay. And of course, we won't get into what is considered suitable for use as service equipment, because if that was the case, then this piece of equipment would only be used for service equipment. Okay, if it says suitable only for use as service equipment, that typically will have the main bonding jumper in there. Okay, so again, that's for another episode, but that is interesting to look at that and understand that some equipment is only for use service and some is not. Okay. All right, let's kind of go down. So here's the green screw. No sizing. It's green. It's not sharpied like the Grunberg likes to do with his Sharpies. But there you go. You can see it. It's evident. No sizing required there. Done. And of course, let's go on and go to some more. So let's talk about, we looked at all this. We discussed this. So real quick, even though it sends us to 250-102C1, we haven't done that yet. So let's look at an example here on the screen, just so you can kind of understand how it works for parallels and how we're going to slowly start to see how table 250-102C1 works. Okay. So if we have a situation where we have a piece of equipment, let's say a service equipment, and it says the ungrounded copper conductors of 1100 kc mil or smaller, or ungrounded aluminum conductors 1750 kc mil or smaller, so keep these numbers in your mind, simply determine the largest circular mill area of the ungrounded conductors. Then you refer to 250.102C1 for the minimum size of the main or system bonding jumper. So I'm doing this, and then we'll jump and give you an example. So let's say we have an 800 amp service, and it's being supplied by two sets of 500 kc mil. So I got two raceways. I got conductors in raceway 1 and conductors in raceway 2. They're in parallel. So I've got 500s in this one, 500 in this one. These happen to be XHHW conductors, and they're installed in parallel. So you're only going to take one phase here, folks. You're not going to try to add all of them up. Let's just say phase A for argument's sake. You're going to take A's and add them up. So the two 500s, it's going to be 500, 500. That is 1,000. Now, that's not 1100 or over 1100. So we're just purely going to use the table. We just go right to the table if that's the case. Okay. So if that's the case, then it's pretty simple, right? So we'll go to the code, back to the code, and let's jump. And let's see if I can get that right. So I'm going to go on and move us down to that. So that's what we're working on. And by the way, in some of the forums, they posted 250.66, probably in an old code book, I don't remember, might be 2008 earlier, that used 250.66 for not only the grounding electroconductor, but also for use with sizing bonding jumpers. That is not the case anymore. So go right on past this 250.66. That's grounding electroconductors. It's not what we're working on. We're going right here. So 250.102C1. Okay, and we're sizing the main bonding jumper here. So in our case, it was what? It was 500 and 500. It was parallel, which is what this language means right here. See, it says equivalent area for parallel conductors. Okay. If it's just one conductor, if it's one raceway and it was 500 kc mil, then you just go down here. If it's copper, it'd be over 350 through 600. Then it would be a 1/0 main bonding jumper, or a 3/0 if it's an aluminum main bonding jumper. Now, up to 1100 kc mil, you don't have to worry whether or not the bonding jumper is copper and the supply conductors are aluminum. It doesn't matter, okay? So you always will use this table when you're sizing that main bonding jumper. You don't have to worry as long as it's not over 1100, okay? So if it is aluminum 500 kc mils coming in, one set, and it's a copper main bonding jumper, then it's simple, right? You go right to this table, and you go, does it fall between over 350 through 600? Yes. But if it's aluminum conductors coming in, it's over 250 through 500, okay? So we'll be right here, right? Because we said it was 500 kc mil. Then that means if your main bonding jumper is copper, then it would just be a 2. Good to go. That's simple, right? Or if you want to stay with the side of the material that the main bonding jumper is, you said it was aluminum, you want it to be aluminum because your supply conductors are aluminum. Okay, that's your choice. Then you can go with a 1-aught aluminum, okay? Where this might come into play, or where you might get where you have aluminum conductors coming in and a copper main bonding jumper, is because of the price of copper has gone up. And so, in a lot of services coming in are the aluminum, and they come in, they terminate at the main breaker, and then everything that comes, say the panel, you have 2 separate buses like we showed in that illustration, and they use copper to connect the 2, right? And so now you've got a main bonding jumper that is copper, but you've got aluminum conductors coming in. Now, as long as it's not over 1100, then you don't have to worry about what we're going to talk about in note 2. You don't have to worry about it. You're okay, right? So you just simply pull from this table, okay? And that's it, right? Now, what happens when it is over 1100? Okay, so let's give us another painted scenario. And we're going to say that our example is the same one that I posted on all of my social media. We're going to say that it is, and to do that one, let's bring up the picture. How about that? Let's bring up the illustration first, and we'll set an example here. All right, so look at this. So this is the picture that I posted on all of our social media. Ignore the given. We're going to use this as an example. Ignore the given right now. If these 3 sets of 750 were copper, and that main bonding jumper that, again, as you can see up here, it's connecting the neutral terminal grounded conductor bus over to the point where the equipment grounds would connect, or where it's bonded to the enclosure, where the supply side bond, where all that takes place. Since that's a wire type, if that's got to be sized, and all the conductors coming in, and those conductors coming in from the bottom there, those are service supply conductors. And the overcurrent device and all that is off to the left. Okay, so that's off. It's not relevant to what we're talking about. It's all part of one big assembly. We want to focus on what's given here. And I like to do illustrations that make you focus on what's here. So if the conductors coming in were copper, and everybody got this right, then if it is over 1100 copper, then you're going to use note 1, which is, and of course the table tells you that. We go back and look at the code. Notice what it says at the bottom. I know you can't see it because it's kind of blocked by the spilt coffee here. There it is right there, over 1100. Then you see note 1 and note 2. Well, if it's copper supply conductors and the bonding jumper, main bonding jumper is copper, then this is easy. Then all you're going to do is do exactly what we did. Take all of the sets and add up just one of the phases. And that's what it says in the note. And then you take that by 12.5%, right? Which is 0.125, because I like to work everything down into a decimal. Makes it easier to function, okay? So if we go back into the image, trusty calc, this one be easy. If it's the 3 this one, you only take one, this one, and it's 750. So we're going to take 750, which is 750,000 circular mils. And I'll get your question, Andre, don't worry. We do this times 3. That is 2,250,000 circular mils. Well, what does note 1 say? And again, copper bonding jumper, copper supply conductors. Easy peasy, right? Should be easy peasy for us, okay? So let's go look at what the note says. We'll scroll down a little bit. So note 1 tells us, that says, if the ungrounded conductors are larger than 1100 kc mil, copper or 1750 kc mil aluminum. It says the grounded conductor or bonding jumper. And the reason it says or bonding jumper because the premise of this table is covering multiple types of bonding jumpers. Main bonding jumper, system bonding jumper, supply side bonding jumper. So it's a table covers a lot. So that's why it says it that way. It says, shall have an area not less than 12.5% of the area of the largest ungrounded supply conductor, okay, or equivalent area of parallel supply conductors, okay? So we are taking just one phase and add up all the A's, and so that was 750, 750, 750. We added them up. It was 2,250,000 circular mils. We take that and we multiply that by 0.125, and that gives me what? What does that give me? Somebody out there, let's see if somebody out there can post that in the question. What does that give you? If we were doing it 750 coppers, okay? Let's see who posted out there. Anyway, if that was the case, and I'll belabor that. So 2,250,000 times 0.125, that's 281,250 circular mils, right? So where are we going to, now we don't even have to go to chapter 9, table 8, because we know that circular mils go in this. They go 250 to 300, like that. So, but if you wanted to go look, then you would go to chapter 9, table 8, and you look under the circular mill, and you have to have one that's at least 281,250. So this would be, 250 kc mil wouldn't work, right? It would have to be what? A 300 kc mil. That's what your main bonding jumper would be. That is if those were 750 coppers. You with me? Okay. And a lot of people posted that. And it was a valiant effort because that is exactly what you would do if all of them were copper, right? So the question that we presented, however, was what do you do when the main bonding jumper is a different material than what the supply conductors are? So here's where we're getting to that one. So note 2 on the screen. Let's read it really quick, and I'll show you how this works. It says, if the ungrounded supply conductors are larger than 1,100 copper or 1750 kc mil aluminum, and if the largest ungrounded supply conductors and the bonding jumper are different materials, okay, when it says that, it says, one's copper, one's aluminum, okay, or one's copper clad aluminum, or whatever, different materials. It says the minimum size of the grounded conductor, or in our case, the bonding jumper, shall be based on the assumed use of ungrounded supply conductors of the same material as the grounded conductor or bonding jumper, and will have an ampacity equivalent to that of the installed ungrounded supply conductors. Okay, that's a lot. That's a mouthful. Let me break it down in simplistic form. If I've got aluminum conductors coming in and I got a copper main bonding jumper, I have to say, what is the ampacity of those aluminum conductors? And I need to find the equivalent in copper, right? I need to find the equivalent in copper because that's what the material is on my main bonding jumper. So how do I do that? Well, the first thing I have to do is say, okay, well, let me just do one conductor because obviously I'm going to do that times 3 anyway. So one conductor. So if I'm choosing my equivalent in copper, I got to go to 31016. I need to know what the ampacity is of an aluminum 750. Now, the next question people ask is, do I use the 90? Do I use the 75? Do I use the 60? Which do I use? Well, you don't use the 90 because a 90 is only used for adjustment and corrections. So we're going to use 110.14C1A and B, and B tells me I'm going to use, since it's over 100 amps, I'm going to be using 75 degrees C. The other reason is, in this illustration, I don't tell you what the ratings of the lugs are at all. Now, if all of these lugs were rated 90 degrees, everything was rated 90, and it was stamped on those lugs, and you can argue that, well, all lugs on a bus bar are rated 90. I didn't tell you that. So this is when I talk to my students, and I tell them, don't assume anything unless they give you that in an exam. In the real world, what you're going to do is you're going to look at the rating of the lug. Make sense? But since I don't give that to you, you don't know So you have to follow the rules of 110.14C1A and B, and that means you're going to use 75. So I'm going to go to table 31016, and I need to find out what the equivalent would be to that of the 750 kc mil, right? So let's do that. So I'm going to get my code book here, and I'm going to go over to that. Bear with me while I jump there. You got your code books, do it with me. Go to 31016. And this, by the way, is a step that everybody got wrong except for David and a select few that were actually on our Wednesday night training session last week, or this past Wednesday. We do that every week, Wednesday nights. If you're in the Fast Tracks program, you can come to a live sessions and ask me anything you want. And Yo was in there, and he's the one that asked this question, and it's what spawned me to want to do some training. So anyway, here's the aluminum, and let's see, make sure I'm not cutting off the screen. No, I'm good. Okay. So I always have to check to make sure I'm not cutting anything off. All right, so 750 right here is 385 amps. Okay, so remember ampacity in the equivalent to that 750. So now we're going to be looking at copper. Remember, it said assumed the use of the supply conductors as the same material as would be the bonding jumper. That's why we're going to assume, even though they're aluminum, we're going to play and pretend that they're copper. And what size would they need to be? Well, if 750 is good for 385, then we come over here and we need a conductor that's good for 385. Well, we can't use 500 kc mil copper because that's only good for 380. So we're forced into the 600 kc mil. So that is good for 420. It most certainly is equivalent to 385, and it is greater than that. So we're going to use 600 for this. Now, once we have selected that conductor, it's 600 is the assumed equivalent, okay? Now we can come back and do what? Follow the rules that we did before in note 1, because now the exercise is just like we did before. Everything's copper. Then it's easy peasy, right? We take that 600 and we're using note 1 now to go back and do what we did before, okay? Just an exercise that we had to do. So we're going to go back to the graphic. So in this case, we're doing 3 sets of 750s, but we assumed them based on note 2 of 250.102C1 in the notes of the table. We actually are going to use the 600, and we do it just like what we did before with note 1. We do 600 times 3. Okay, so we'll do 600. So it's 600,000 circular mil times 3, and that's 1,800,000 circular mil times 0.125 equals 225. So it's 225,000 circular mils. So now that main bonding jumper has to be at least 225,000 circular mils based on our assumed copper equivalent to what's given in the table, okay, or in the graphic. So now we got to go to the code, and we're going to go to table 8. So let's do that and work this thing out. So I'll go back to the top, and I'm going to go down to chapter 9, and we're going to go to table 8. If I can hold on here, I'm not sure what happened to my stuff here. Bear with me. Bear with me. Chapter 9, table 8. Okay, so you should see this on the screen. And we're going to scroll down. And what we got is, well, we're looking at circular mil. Say a 4-aught is good for 211,600. That's not going to work. The next size up is 250 kc mil. And when you see the 250 here, again, this table is based on the circular mils up to 4-aught, which is basically American wire gauge. And then once you get to 250 and larger, that's the circular mils. And so 250 is 250,000 circular mils. So we needed to be at least what? 225. Well, we're going to have to use a 250. So to answer this question that I've been asking on all the social media platforms, how you size this, that main bonding jumper would have to be a 250 kc mil based on the assumed copper supply conductors using note 2. How many knew that? And based on the number of people that answer it over in the social media, not very many answered that correctly. So that's how you would size it that way. Now, we're going to do some upcoming episodes. Hopefully you enjoyed this. We're going to do some upcoming episodes for supply side bonding jumpers. In this case, it would be sized the exact same way because we're using a daisy chain method where we're actually looping through them. So you have to count for every conductor in each raceway. If it had been what's called an individual, then it would have been a single one over to each raceway, and you would size a supply side bonding jumper based on the size of conductors in each individual raceway. But here we show the daisy chain option. That's going to come up in future episodes. If you're excited about grounding and bonding, I encourage you to get our grounding and bonding course. It covers a lot of information. Everything from equipment grounds, supply side bonding jumpers, to understanding the difference between whether or not you use, downstream and the separation in accordance with 250.24A5, how you have to have a separated, isolated neutral downstream. Covers all of those things, explains the grounded systems, ungrounded systems, high impedance systems. All these type of things are covered in the program. If you're interested in that, check it out on our website. It's on electricalcodeacademy.net, so check that out. Okay, so that's how you size the main bonding jumper. And remember, if it was 1100 kc mils and less, then you just simply go to the table. If it's copper supply conductors and copper main bonding jumpers, and it is over 1100, then you're going to use note 1. It's just 12.5%. If the main bonding jumper is copper and the supply conductors are aluminum, you have to redo that by assuming those aluminum conductors are copper and redo it. And then once you establish the right size as copper that are equivalent to the aluminum, then you go back to note 1 and just do the 12.5%. Wham, bam, thank you, ma'am. Done. So it really is that simple, but I thought it would be a great lesson to have a coffee hour. And I was going to get into other topics, and I know coffee hour sometimes tends to be, a little over an hour. So I'm going to answer some questions, and I will talk about different conductor types if you have any questions on those. For example, the difference between THHN, THWN-2, XHHW-2, USC-2, RHW, PV. If you have any of those questions, I'll answer those since I'll do a separate episode on that. But in the chat, if you have a question on any of those things, go ahead and ask them. I'll do my best. So let me see if I can go back now and see what other questions we have, because I want to make sure I answer some of these. John says, I've already had the first pot since 4:30 a.m. John's up early. You know that old saying, California, I don't know where you're at, John, but you did tell me, but I forgot. California people, if they get up at 9 or 10 o'clock, I guess it was Steve Harvey that said it, your day's already over because the stock market started and everything, but it is a weekend, so no stock market. Let's see here. Let's see here. Let me go here. Oh, John says he used designated ground screw spray paint. I hear you, John. Let's see here. Andre, let's see. Your question was about sizing the EGC for a feeder tap. Do you size it off new conductors being tapped or up to the main tap feeder conductors? Okay, so tap conductors, you're going to want to look at feeder tap allowances in 240.21. To answer that question, so 240.21 for taps. If you go into taps and you look at, let's see here, bear with me here. Look, because there was a specific area that I'll send you to. It was a specific area I was going to send you to. So long and short, that basically, typically you tap it doesn't have to be larger than the conductors that are tapping from the feeder. So you would tap for the feeder. So a lot of times the tap will have no overcurrent protected device at the tap. So you're going to base it on from the point where you tap and the overcurrent device that you'll be supplying from the tap. So you want to make sure that the equipment ground's there. It never has to be larger than the size of the tap conductors. Okay, so that is a rule that's over in 250.122. So if you go to 250.122, just for craps and giggles, and if we look here, if you got your code book, I'm sure you do. Let's go to 250.122. And let's see here. So you see all the sizing that you have in 250.122. Okay, following all down, you'll see there's a feeder tap in G. The feeder, it says equipment ground conductors installed with the, or should I go on the computer? Hold on, let me go to the code. I'll go to the code. Let me go to the code real quick. And anybody's got other questions, feel free to type them in. I'm gonna go back to the code for this one. Scroll down to it. And don't worry, I'll get your questions. I can. And I don't use the search feature because this is just an online version. So this is my version that I use. So just getting you dizzy, I apologize. Okay. All right. So G says equipment grounding conductors installed with feeder taps shall not be smaller than shown in table 250.122 based on the rating of the overcurrent device ahead of the feeder of the supply side, or on the supply side ahead of the tap, but shall not be required to be larger than the tap conductor. So what I was saying was, typically because of the tap rule and because of how you're tapping, typically when you tap a feeder, they're not the same size as the feeder. The conductors, the tap conductors aren't the same size. If it was, then is it really a feeder tap? If it's the exact same size as the tap conductors, then to me, it's just an extension of those conductors. The whole premise of a tap and using the tap rules in 240.21 is to be able to tap it with a smaller, potentially a smaller conductor, provided you meet all those rules, that you're tapping it, but typically it can't be smaller than what would be required per this table for the feeder, but usually those tap conductors are what? They're smaller than the feeder. So it's not required to be larger than those tap conductors, that type of thing, okay? So because the feeder is probably going to be a bigger overcurrent device anyway, then that would result in a bigger equipment grounding conductor. So you're probably going to just size it the same size as your tap conductors, okay? So hopefully that answered that question for you. Let's see, where are we at? What other questions do we have? Did I miss any? I know, Andre, it's fine. Not any question, you can bring anything you want. If I don't know the answer, I will tell you. Basement King says August 1st he'll be registering for the CMECP. Hold on, I do have something for that. Hold on. I hear you. Let's see here. What does James say? Lots of old systems here. We separate grounds and neutrals on most remodels and add ground bars, sometimes the neutral bars, where there are not enough. Yep, absolutely. Sometimes you won't have enough terminations and you will have to. Typically, most of the panels, let me come back to me, unless we need the code again. Typically, most of the panels are going to give you enough lugs you need, but if you are doing a remodel or retrofit or something, then you might be adding circuits. Then, again, provided you're not exceeding the number of overcurrent devices that can be in that panel, then you might not have enough lugs. So there are extensions and things like that, okay? Second thing. Let's see here. James says, question, this seems to clear up transient noise and objectionable voltage, you mean objectionable current. Does it make a big difference? There's got to be another piece to that. Well, the separating downstream of the neutrals from the cabinet, so you don't have what's called a case to neutral connection. Well, that's required by the code because what that does is it creates circulating current. And so it creates energized parts. And if you happen to lose a path back to the source, it could travel, or you lose one of the conductor, it could travel on these non-current carrying parts, and it becomes a hazard. And be honest with you, if you put a main bonding jumper in, the screw in a downstream remote distribution panel, then you are going to have current circulating. And it can create noise, okay, objectionable currents. Now, noise is not necessarily objectionable current, okay? It's a nuisance. Objectionable currents can be dangerous, and the noise is not, okay, really that, but it does have an effect on how certain equipment can operate, and so it does become a problem. So you're supposed to make an effort to reduce objectionable currents. And but your question more about the EMF or the electromagnetic interference and all that kind of stuff. Yeah, one of the things that you want to do with this separation is, again, you have a very defined position where the non-current carrying metal parts are not going to be energized unless there's a ground fault condition. Then they do get energized and they become part of like a current carrying conductor when they are energized, but other than that, they're not. So that's why it's so important to make all the connections back to the source so properly. You know, proper fittings, proper connections, proper couplings, make sure they're wrench tight, do everything so that you have the integrity of that equipment grounding conductor or ground fault current path. The effective ground fault current path is intact. The neutral, you want isolated downstream, but yeah, bringing them together is more of a touch hazard, potential hazard, but it will also create the noise, and people don't want the noise, that type of thing. Let's see where I need to step up my game as well. yeah, you've been slacking. I will remind you now, Swartzy comes to every Wednesday night, Grunberg, and he is dedicated. He's focused, laser focused. I don't know what happened to Grunberg. I don't know. Let's see here. Let's see. Jesus, I guess, says, or is it Jesus? Or, you know what? Is it Jesus? Or is it Jesus? Anyway, so I'm going to take my journeyman's test this fall. I just bought your Fast Tracks program. I'm excited to work with it. Absolutely. Make sure you try to attend some Wednesday nights, although we do record them. But make sure you join in and jump in and come to one. They're not required. They're not part of the Fast Tracks, but you can join in. And I encourage you to do that. And make sure you do those competency reviews. Make sure you watch the folder at the very top to learn how the program works. Definitely want to watch that. What do we got here? Andre says, my co-worker is saying you just had to use 250.22, so it would be lower size, only size to the new conductor, and didn't think that was right. Oh, so you... well, 250.122 is based on the size of the overcurrent device. So you would have, since the only overcurrent device that's ahead of that tap is the feeder overcurrent device. So that's why 250.122G says that you use that, because the whole premise of the table 250.122 is based on the overcurrent device size. The whole reason that we do tap rules is because we don't want to put overcurrent protection at the tap. That's the whole reason we do it, right? So to size an equipment ground from that tap, it would either be sized based on the overcurrent for the feeder, which is what's running in the, that'd be fine. But it doesn't have to be larger than those tap conductors. So if you're tapping and they happen to be 12 gauge or 10 gauge or 6 gauge or whatever, then that equipment ground would not have to be larger than whatever those taps, okay? So set him down, educate him, and actually, when you read it to him, make him think, wait a minute, since it's supposed to be sized based on the overcurrent device in table 250.122, where is the overcurrent device? It's upstream. What is it? It's the feeder. So does that mean I have to size the equipment ground, even the tap, based on that? Yeah. But it doesn't have to be larger than the tap conductors. So kind of the way they think about it. Now, it's funny, you said that he says they tap into overcurrent, but that's going into the supply side of the overcurrent, right? The overcurrent does what? It trips what it sees on the load side, not on the line side, right? So his logic wouldn't make sense. You're right. You're absolutely right. Oh, let's see. Joseph from New Jersey. Thanks for Joseph. Joseph always goes listening from New Jersey. Are you an electrician? Is he always listening from New Jersey? Thank you for listening. All right, so if we don't have any more questions, coffee hour did go over a little bit today. Not too bad. Only about 8 minutes or so, but hopefully you got something out of it. And hopefully you'll join me for the next coffee hour. I don't know the topic yet, but it'll be a good one. And hope you all have a wonderful week, and look for new videos to come out soon. If you want to support us with a monthly subscription, visit our website, and you can do that. We appreciate everybody that subscribes. And if you want to take the Fast Tracks program right here, check us out. You can get there by going to electricalcodeacademy.com.net.org, or you could go to fasttracksystem.com if you want. Many ways lead you there. Tell other people about our programs. I'm here to help you. Once you become a student of ours, you become a friend. You get to also get into Sparky Hub. And there you can post all kinds of stuff in the Sparky Hub. We have great conversation. In fact, the answer to today's question, that image that I shared on all those social media, the answer to that was already in the Sparky Hub. It was already there. So if you went there and you joined it, you would have seen the answer before today's show. And if you were in our Wednesday night sessions, our live streams on the Zoom, then you would have already known how to do this. That's the advantage of becoming a member of the program, and basically becoming a member of the Fast Tracks family. Okay, so that's it for coffee hour. A little over today. I appreciate all of you that joined me. Everybody take care. God bless, and have a safe week. Again, electricity kills, and we have to give it respect. Okay, don't be one of those that goes on TikToks or Instagram and makes those little tripper where they take a piece of wire and stick it in it. Don't be stupid. Be smart. You're a professional. Treat the trade with profession. Anybody that does that kind of crap, feel free to jump on them, and let's keep it high class. Okay. Sometimes I drop low bar, but keep it high class. Again, until next time, everybody stay safe. God bless. I appreciate you all. Take care.
Morning coffee, vanilla latte, sip to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte, sip to go. I drink it slow. Morning coffee, cappuccino.